Afternoon and evening Bearcats. This is Ms. Zorn, and we are going to talk about 9.5 Binomial Theorem, which will be on your next test, which has been moved to a week from tomorrow, or Friday the, whatever that is, 26th, 27th, something like that, whatever that Friday is. Hold on just a second. Yes, Friday the 26th. Please make sure that you have done your review that was handed out on a little slip of paper. For my students, and I guess any students, I will also post that little slip on LMS, and I will also work out the review sometime midweek for all you tax testers who are not in class to go over the review with you. All right, I hope that you are all having a great tax week and are doing well. I will be in my room, to my class, I will be in my room in the afternoons from 5th period on next week, all week, so you can come by anytime if you have questions. You can also email me. Alrighty, here we go. I want to start with something that we're familiar with. Binomials. Binomials, we're familiar with binomials. We know what a binomial is. Let's just take an easy one here. Let's take x minus 3 squared. Okay, this is a binomial squared. And we have a shortcut we've been using all year for binomial squared, and let's take a look at that again. Remember, we would take our first term and square it. We would take all the two terms plus the exponent and multiply them all together. So it'd be 2 times x times negative 3, which would be negative 6x. That would give us our middle term. And we would take the last term, negative 3, and square it, and negative 3 squared would give us a positive 9. And this would be the expansion, what we would call the expansion of that binomial. Truly, we just multiplied it out times itself. We FOILed it, if you want to think about it. We did this. We did x minus 3 times x minus 3. And I know I'm going through this because I want to make a point at the level of effort and details you would have to go through to get these if you don't have a shortcut. So if we didn't have a shortcut, we would FOIL x times x is x squared, x times negative 3 is negative 3x. Then we would have to go back and go negative 3x is negative 3x, and negative 3 times negative 3 is a positive 9. Then we would need to combine like terms, and we would get x squared minus 6x plus 9. All right, so we get the same thing, but this is much more efficient and much quicker to know. We are going to go on now, and I want to ask you, what if this binomial x minus 3 had been to the 7th power? Wow, that means we would have had to do x minus 3 times 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 x minus 3. Wow, what a lot of work. FOIL, and then we would have to FOIL, and then we could FOIL these, and then we would FOIL these together, and we'd FOIL these together, and we'd have to still multiply by this, and then we would, I mean, it would take us a lot of time, and there would be many, 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 many places to make careless errors. So, there is a shortcut for doing this using patterns and something called the binomial expansion. Binomial expansion. I want us to look first at the pattern. After we look at the pattern and understand the pattern, then I'm going to also give you a shortcut to the pattern. So it's like a shortcut on a shortcut, or I sometimes say it's a shortcut squared. All right, here we go. So let's take a look at this pattern. All right, when we look at this pattern, we're going to let n equal, and I'm going to show you what it equals in a minute, but let's just look at the pattern. We would have binomial to the 0 power, x plus, let's just use plus y, and that would equal 1 because it would be to the 0 power, and so our n value would be 0 in this case. Anything to the 0 power is 1. Then we would have x plus y to the 1st power, and of course that would just be x plus y. Then we would have x plus y squared, and we've done that before. Let's just use that little binomial shortcut again, and again this time n would be 2. And so we would have, let's take the first term and square it, multiply everything together, which would be positive 2xy, and then take the last term and square it, which would be y. All right, and that's a binomial squared, and we have a shortcut. Now we get tricky. So we have x plus y cubed. I'm not going to go through the math, but I'm going to show you what the result would be, and we're going to look at the pattern. This would end up being x cubed plus 3x squared y plus 3xy squared plus y cubed. Let's keep going. What if we had x plus y to the 4th power? Well, to the 4th power, it would be x to the 4th plus 4x cubed y plus 6x squared y squared plus y to the fourth. And let's do one more, and it would continue. I'm not going to continue, but I will go ahead and go to the fifth power. And I'm just going to put these dots because this would all continue in the same pattern. So we would have x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed plus 5x y to the fourth plus y to the fifth. And these patterns would continue. Notice it makes a triangular pattern as well. It gets larger as it goes further. Couple of things we want to examine in this. The first thing we want to examine that the number of terms is equal to n plus 1. And we said n were these these exponents. So 0 plus 1 is 1, and that's one term. 1 plus 1 would be 2, and we have two terms. 2 plus 1 would be 3, and we have 3 terms. 3 plus 1 would be 4. We have 1, 2, 3, 4 terms. You get the idea. So the exponent means that the number of terms in your expansion will be one more than that. One more than that. Just to tie something from the past, and remember that the exponent, one less than the exponent, was the number of turns in a graph, in a polynomial graph. And one more are the number of terms in the actual expansion. So there's a couple of things we can relate there. All right, the next thing I want us to know is the powers of the variables. The powers of the variables. In the first one, everything's just equal to 1. But this is a x power of 1 and a y power of 1. Now let's look at the pattern. X, the power of 2 would be from this exponent, and the next x is just a power of 1. And then it would be x to the 0, which is just 1, and it kind of goes away. Notice here we have x cubed, and then x squared, and then x to the first, and then x to the 0, which you don't see because it's 1. And then x to the fourth, x cubed, x squared, x 0. We would have x to the fifth, x to the fourth, x to the third, x squared, x to the first, and then like 0. So notice that the powers descend for the first term variable. So I'm going to say powers, descend, D-S-C-E-N-D, I think. You know I don't spell well. The powers descend from the first term variable. I'm not sure that makes sense, so you may want to write those words and it makes sense for you. Now let's look at the second variable in our problem and what happens to those. Okay, again, everything's 1. Again, they're just 1 and 1. Look at the y. It'd be like y to the 0, y to the first, and y, squared. Missed that. This would be y to the 0, y to the first, y squared, y cubed. Y to the 0, y to the first, y to the second, y to the... I think I missed something in there. I did. I missed a term in here. This should be... I went too fast. That should be plus 4xy cubed. See, this little pattern helps me catch my mistakes. So you would have y to the 0, y to the first, y to the second, y to the third, y to the fourth. And in the last one, you have y to the 0, y to the first, y to the second, y to the third, y to the fourth, and y to the fifth. So the powers ascend or increase by 1 for the second term variable. So I'm running out of room here, and I want to get all this on one screen. So the powers ascend by 1 of the second variable, the y value. And it doesn't always, it's not always x and y, but there'll be two variables because it's a binomial. All right, the next thing is that the sum of the powers for each term equals n. All right, so look, the sum of the the powers for each term. Not the total, but each term. So this is 2. Look, this is a power of 1, and this is a power of 1, which is 2, and that's 2, and that exponent is 2. This is 3. 2 and a power of 1 is 3. 1 and a power of 2 is 3, and that's 3. They all add up to 3. So let's go down to this last one. That's 5. The power of 4 and the power of 1 would be 5. The power of 3 and 2 together would be 5. The power of 2 and 3 together would be 5. The power of 1 and 4 together would be 5, and that's 5. So the power for each term adds up to the binomial term power. All right, so that's another pattern. Now, look at the coefficients. Those are the terms in front. Notice there's a 1 here. That's all they have. And notice that that's really a 1 and a 1. And notice this would be a 1 and a 2 and a 1. And this would be a 1 and a 3 and a 1. And this is a 1, a 4, a 6, this should be a 4 and a 1. And let's look at this last one. It helps us in this last one. This is a 1, a 5, a 10, a 5, and a 1. There's a pattern, and there is something that helps us remember the coefficient pattern. Okay, so that's what we're going to have to add in, those coefficients. We're just going to put those in this place. I'm going to change screens here. I'm going to rewrite this last expansion so that we can look at it in terms of this little helpful hint for our pattern. Okay, this was our last expansion we had. X to the 5th, 5x to the 4th, y to the 1st, 10x cubed, y squared, 10x squared, y cubed, 10x to the 1st, y to the 4th, and y to the 5th. And we've already talked about the patterns. Let's look at those coefficients again. The coefficients for the first term is 1, and then we have a 5, and then we have a 10, and then we have another 10, oops, and that should be a 5, and then we have a 1 again. Okay, so those are our coefficients. There is something called Pascal's triangle, and you may have heard of this before. It's called Pascal's triangle. And we're going to think of this as row or term 0 to start with. For term 0, that would be a power of 0. Anything with a 0 power is 1. Our triangle would have a 1 at the top, which means in our previous screen, the very first thing was equal to 1. All right, equal to 1. In row 2 or term 2, in the squared, I'm sorry, 1. So the binomial to the first power, we would have a 1 and a 1. The binomial in the second power, we have a 1. In the middle, you add the two terms from above. So 1 plus 1 is 2 and a 1. For a third power, we have a 1. We add 1 and 2 and get 3. We add 2 and 1 and get 3 and a 1. For the fourth, we have 1. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4 and 1. And finally, and we would continue this pattern, but the fifth one, the one we're talking about, notice we have a 1. 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is 10. 4 and 1 is 5. And then 1. And those are where our coefficients come from, and that makes it really easy to know the coefficients. All right, now we have all this information. Let's try to expand something using these patterns. All right, we're going to do two examples with this expansion. The first one we're going to do is just a very simple one, a binomial to the fourth power, x plus 2 to the fourth power. All right, first I'm going to write Pascal's triangle over here really quick and get the fourth row. Remember the top row, though, is 0, and that sometimes it's easy to forget. So I really want 0, 1, 2, 3, 4. I really need to hear. So it's 1 and 1, and I know it's 1, 2, and 1. And then it's 1 and 2, and 1 is 3, and 3, and 1. And the fourth row is going to be 1. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and 1. So these are the coefficients I'm going to want. And that's the first thing I'm going to write down. So I'm going to write 1, 4, 6, 4, 1. Because this is addition, I'm just going to put a plus sign between all of the terms. And actually that plus sign, oops, I should do this. Oops. I should put the plus sign near the thing because that's where we're going to add to. All right, so I put the plus signs in there because they're all going to be plus signs. Now what I'm going to do is I'm going to go by that pattern we talked about earlier, I'm going to start with the first term, x to the fourth power. So it would be x to the fourth. And the second would be x cubed, x squared, x, and then x to the 0, which is just 1. I'll go ahead and put it just so we realize that becomes a 1. Then I'm going to do the reverse. I'm going to take the last term and I'm going to go descending pattern. So I'm going to have 2 to the 0 power, 2 to the first, 2 squared, 2 cubed, and 2 to the fourth. All right, and now I'm going to kind of simplify this. So I have 1 x to the fourth and times 1. So I'm going to go ahead and do that term. 1 times 1 is 1, so I just have x to the 4th. So I have 1 times x to the 4th is x to the 4th. That's my first term. Plus, I have 4. I'm going to do that up here. 4x cubed, and 2 to the 1st is 2. Now, 2 times 4 is 8, so I'm going to have 8x cubed. Next, I'm going to have 6x squared, and 2 times 2 would be 4. 4 times 6 is 24, so I have positive 24x squared. This is a big pattern you're learning here. 4x, 2 cubed is actually 8. 4 times 8 is 32, and that would be x. Plus, I have 1, oops, x to the 0 is 1, and 2 to the 4th power is 2 times 2 is 4, times 2 is 8, times 2 is 16. And so I would have positive 16 at the end. And that would be my expansion. That would be my expansion. All right, now let's beef this up a little bit and do another example where the number, there's coefficients in here in front of our terms. And more letters. All right, we have 3x y to the 4th. Again, I'm going to do my Pascal's triangle. Remember, I started at term 0 or 0 row, so I'm going to put 1, and then I have 1, 1. That's the first, second, third. I need the 4th row because of this exponent. And so I have 1, 2, 1. I have 1, 3, 3, 1. And I have 1, 4, 6, 4, 1. So I'm using these again. So I'm going to write them down. 1, 4, 6, 4, 1. And I have subtraction this time. This is really, really important. If I have subtraction, I'm going to start with a negative, then a positive, then a negative, then a positive. Start with a negative and alternate your signs. That's very important. That's also a pattern. All right, the next thing I'm going to do is I'm going to put these coefficients in parentheses because it looks like I'm going to have a lot more to multiply this time. All right, I'm going to have the first term, which is 3x to the 4th power. So I'm going to write 3x to the 4th power. And I'm going to write 3x to the 3rd power. And then I'm going to write 3x to the 2nd power. And then I'm going to write 3x to the 1st power. And then it'll be 3x to the 0, which is 1. So I'm just going to go ahead and put 3x to the 0. But I'm going to immediately cross out and put a 1. All right, now I'm going to take my y value. And I have negative y. Be careful. And I would have to the 0 power, which I'm cross out and make a 1. I would have, I don't know, not negative y, just y, sorry. Then I would have y to the 1st. I would have y squared. I would have y to the 3rd. And finally I'd have y to the 4th. All right, let's go ahead and clean all of this up. So be careful, 3 to the 4th power. That would be 3 times 3 is 9. And 9 times 3 is 27. And 27 times 3 would be 81. So I would have 1 times 81, x to the 4th, and then the y to the 0 was 1. All of that would end up being 1 times 1 would just be 81, x to the 4th. That's really important. Then I'm going to say minus down here, and I'm going to calculate this. I have 4. I have 3 cubed, which was 27, x cubed, and then I have y to the 1st. So 4 times 27, 4 times 7 is 28, carry my 2, 2 times 4 is 8, 10. 108 x cubed y plus, and we're going to keep going. This time I have a 6, 3 squared is 9, and I have x squared, y squared. 6 times 9 is 54. X squared, y squared. And notice my coefficients all add up to 4, which is when you add the term coefficients up, that's important. Then I'm going to say minus, and I have 4. 3 to the 1st is 3x, and then y cubed. So I would have 4 times 3 is 12x, y cubed. And then I would have plus, and that's a 1, and that's a 1, and I have y to the 4th, and so I have y to the 4th. And that would be my expansion. And that is way, way shorter and way, 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 way easier until than it would be if we actually had to mark them all out and expand them. Okay, Bearcats. One last thing is we want to talk about binomial theorem. And the binomial theorem can be used if we just want to find a coefficient, a missing coefficient, a particular one, and you didn't want to go through the whole, and maybe it's a really large one, it would help us do that. So let's take a look at this situation. And the binomial theorem looks like this. Little n, c, with a subscript r. And here is the actual theorem, and you're going to want to have this written down. It's n factorial, which you saw in a video previously, times n minus r factorial times r factorial. And we can use this to find a missing coefficient. Let's say it's a very large power of our binomial, and we want to find, the 120th coefficient. So let's take a look at how this would work. Okay, sometimes this is also written with a C, and you have the little n over r, or C n over r. And you'll sometimes see it written like this, and that replaces this value. Notice that I just want to identify for you what each of these pieces of this mean. This is a combination of things taken at out at a particular time. This is used also in probability. Combined, this is a combination. And in this example, if I give you an example, C, and let's put it a 12 and a 5. So it's out of 12 things taken 5 at a time. That's what this would mean. This would be a combination of you have 12 items taken 5 at a time. So how would we calculate this particular coefficient? Here's what you would do. Remember, we're going to use our factorial. The n is the 12 and the 5 is the r, and that makes sure you have that down. So you would do 12 factorial at the top, so 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5, and I'm going to stop because of the 5 in the bottom for a minute. This would continue. In the bottom you would have 12 times 11 times 10. Oh, I'm going to stop because look what happens. All of that would be exactly the same as the top. Would be exactly the same as the top, but we've got to be really careful. That's not what this says, and this is the most common mistake that you'll make. I'm going to cross this out. That's what you'll do. It's n minus r, so it's 12 minus 5 factorial. 12 minus 5 factorial is really 7 factorial. So you would have to start with 7 times 6 times 5 times 4. Oh, and look what happens. So from this point on, you could make that cancellation. We still have to multiply times r, and r would be 5 times 4 times 3 times 2 times 1. So we still have this. Now, let's take a look at what we can do from here. We can make some combinations. Let's say we don't have a calculator to put this into. Notice here that we have 12 still up here in the top, and we could make a cancellation at the bottom. If you take 4 times 3, that would be 12. You could cancel that 12 and 12. You have 5 times 2, which would be 10, and you could cancel this 10 and this 10. The 1 is just divided by 1. That would stay. So now you're really left with 11 times 9 times 8. 11 times 9 times 8, and if you did put that in the calculator or even multiplied it out on your own, you would get 792, and that would be the coefficient in that term. The coefficient in that term. Let's look at 2 more examples, and then I think we'll be done for the evening. All right, let's take a look at these 2 examples, and we're going to plug them in. Remember, this is my n, and this is my r, and in the one below, this would be my n, and this would be my r. So just make sure to kind of keep that on track. Remember, our formula is n factorial, n minus r factorial times r factorial. You have to really, if you write that down every time you do your problems, you will have it memorized already. So it's going to be 8 factorial, which is 8 times 7 times 6 times 5 times dot dot dot. It continues. Then we're going to have, remember, 8 minus 2, which I'm going to cross out and make that 6 factorial, and r would be 2 factorial. So let's take a look. So from 6 factorial, from this point on, we could make that cancellation. we can make that cancellation. At this point, we would have 8 times 7 divided by 2. Well, we really could go ahead and make the cancellation because this is just 2 times 1. So 2 would divide into 8 evenly. You could cross that out and make that a 4. 1, anything divided by 1 is going to be itself, so you have left 4 times 7, which is now 28. And that would be your coefficient using the binomial theorem. I believe you'll see something similar on your test asking you to use this theorem. You will want to plug it in and find your coefficient. All right, one last example and we'll be done for the evening. All right, this is just a little different form. Remember I said sometimes it can be represented this same way. This is where it gets hard in math as you move along because the notations can become different for the same information, and then you think you don't know something. You really do know, you just have to know your notations as well. So again, the top value will be your n value, the bottom value will be your r. So let's go ahead and write our formula down. It would be n factorial over n minus r factorial times r factorial. All right, let's plug in. So we would have 10 times 9 times 8 times dot, 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 dot. It would continue. In the bottom, we would have 10 minus 3 factorial and then 3 factorial. Well, 10 minus 3 would be 7 factorial. So I'm going to go up here and add my little 7 in there. So from 7 on, these will cancel out. Now, the 3 is 3 times 2 times 1. Be careful. Make sure you expand it before you start canceling. Since 2 times 3 is 6 and we've already canceled the 6, we can't use that, but we can use them separately. So we could say 3 would go into 9 3 times. We could say 2 would go into 8 4 times and make that cancellation. And as long as you've got a 1 in the bottom, you're good to go, and you would multiply the top. Well, 10 times 4 is 40, and 40 times 3 would be 120, and 120 would be your coefficient using your binomial theorem. All right, have a great evening, and I will see you guys next week. If you're in any of our classes where you're taxing, then please remember we're in our classes in the afternoons. You're more than welcome to stop by and keep checking websites and LMS. Have a great evening. Night, Bearcats.